Now we come on to the next group of use cases, those from healthcare and life science. And this is obviously a very important subset because healthcare is such a um, important part of the economy, and saving money it is so important, and clouds are viewed as critical there. And also, there's been on the sort of research side enormous progress in areas like genomics. And though the feature of that progress is an enormous increase in the amount of computing that is used to process that data. So the first use case comes from a group at Indianapolis, and it discusses the sort of the core features of using electronic medical records. It comes from the Reagan Street Institute as who pioneered electronic records. And they point out that the EMRs are growing in importance as we build clinical support systems which have significant analytic capabilities behind them. And those are integrated with scientific discoveries to aid clinical treatments. And we are sharing health data as much as possible to improve both the efficiency and the outcomes. Because I say personalized medicine is best thought of, or at least one way of thinking about it, is doing the best possible comparison of a new patient to what happened to previous patients, and maybe using the equivalent of recommender systems to find the patients that best match the current patient. Um, so this requires health data, which are by definition is set up as electronic medical records, and we need to be able to link that data between different sources. So we need normalized ways of getting that information and recording the information. That's called having ontologies, which classify all the key things that we're trying to record. And we need to say to make certain that the information coming from between different sources is properly interpreted in a uniform fashion. Then we need to be able to select cohorts, namely um, like patients whose the evidence from which would be relevant. And the net result is clinical decision support. So this particular group has clinical data from a large number of health sources in Indiana, IMPC, which, as I mentioned, this group has pioneered electronic records. There's 12 million patients, 4 billion observations, 20 terabytes of data, and there are around a million new transactions per day. In the future, they expect to use not only SQL or traditional Teradata type approaches, and Postgres, but also NoSQL, MongoDB, to be able to identify the relevant clinical features. Um, and that's going to use the standard web search, TF-IDF, and document technologies, latent semantic analysis, which is related to uh, latent Dirichlet allocation to extract information. Natural language processing is important here, as it is in other applications involving documents, because so much information is captured in documents, and there's so many documents, we need to automate the processing. And then we're going to use large-scale maximum likelihood methods and Bayesian networks to build decisions. So this is sort of machine learning. Then these machine learning models will be able to work in areas such as diabetes, heart failure, and cancer. We will have a diabetes use case later on. So this particular use case 16 introduces a couple of important concepts in its classification. Electronic medical records is a very important item which we do parallelism over. It's interesting to note that the EMRs have one key feature, which is the patient. And being able to collect together all the information for a given patient is pretty important. And sometimes the parallelism will not actually be over individual electronic records, but rather over all of those records associated with a particular patient. We mentioned here the concept of fusion, and that's pointing out that in almost all these areas, we already mentioned this in the military application, you need to integrate diverse data to aid in either scientific discovery if the diverse data comes in science, decision making in our case here, where we have doctors sitting in the clinic looking at individual patients, going back to the back end, health data, running analytics to support their decision making. And this fusion varies all the way from very complex machine learning to do the integration through a portal, which just has different gadgets in it, one gadget for each source of information. Data fusion is one of the less well defined of the areas because its implementation and its actually input is so varied. There's so many different aspects of diversity, and it's different in different fields. The next use case comes from pathology, and it's another image based. So pathology is like an image, MRI image, or some image which is used to diagnose tumors and things like that, where basically you're taking a picture, and that picture is in 2D or 3D, and then you're looking for anomalies in that picture. And that's a classic image processing algorithm. And the feature of this problem, as we'll see, is that some of these images are going to will continue to grow in size. And they're trying to find ways of taking images, classifying the features, using that classification to identify possible problems or non-problems with the entity from which the images came. So again, these images obviously are used for clinical diagnosis. I had an MRI to look at my back. That MRI was used by the doctor to diagnose what to do with my back. The next use case is pathology imaging. Pathology is an important area, and it's another one of these areas which has a huge amount of images. Remember, in the original, I pointed out that this year there's around 70 petabytes of medical images outside not including cardiology, taken each year. So that's a much larger source of data, say, than the Large Hadron Collider, and much bigger than most other sources. So these images are used to support doctors' analysis. An MRI image can help people diagnose what's wrong with backs, and other images have different will have different types of implications. This use case involves a MapReduce-like framework called Hadoop GIS, which is allowing one to build an image warehouse to support the analytics. These are called spatial analytics because images have spatial structure, and then that supports pathology. This particular work was actually done on FutureGrid originally and in prototype fashion. It involves, so you see here, the Hive query engine on top of Hadoop, and it uses HDFS for the data storage. So it points out that you can do 3D pathology imaging by using basically either building things up from 2D slices, and then we can get larger numbers of three-dimensional objects from a single image. So this provides a much larger image space, a terabyte or so, with a terabyte of additional analytic results. And then a particular hospital might have around a petabyte of data. So this is a big data application. The actual results will involve probably machine learning on the particular images to be able to do the classification and things of the pathologies. And again, as these instruments gain in power and the analytics gain in power, we can expect significant progress here. So as I point out here, parallelism over images is a critical big data case, and that's important just because images are bigger than text. I mean, it's the number of, when you have lots of pixels, there's actually the data is bigger, and there's sophisticated algorithms which take a lot of computing, and so text is a much smaller in size. So images are big. That's why they're important in big data. Notice we have parallelism over images and parallelism over pixels with images. So inter-image and intra-image are examples. Actually, the intra-image is actually being fully studied more than inter-image, but it may not be as important, even though it's technically very interesting and actually pretty hard. Another example of a sort of non-text thing, which will come later on in this this group of use cases, is genomics, where we get sequences which also can produce huge amounts of data, which are very big and much larger than typical text data sets. So this concept about imaging being important, and especially for the life sciences, is quantified here, and it just points out that imagery is not only gotten from instruments like MRI images, it's also got, as we'll see later on, from light sources. And so we need to somehow set up an activity which does the best possible job for doing processing these images. And as there's so many of these images, maybe some pipeline and some back-end resource, which is either in a cloud or a supercomputer, is needed to be a bioimaging resource. So that's the idea here. In this case here, that they're proposing to use high-performance computing, but I think they could do the same thing with appropriate clouds. And one needs to obviously not only get the data into the cloud or the supercomputer, manage the storage, run the right algorithms to enhance the images and extract segments and objects from the images, and find either human or other ways of extracting features. And there's our set of image processing libraries mentioned here, which I'm not personally familiar with. ImageJ, Omoro, and Volrover. Now we come to one of the genomics examples. It comes from NIST. They have actually, probably in the scale of genomics, so not a huge data set, but it's very typical of the issues, where DNA sequences produce hundreds or maybe thousands of gigabytes of data per day, and that volume has increased much faster than Moore's law. I showed that slide in the introduction. And proteomics also provides equally large amounts of data, and NIST is 40 terabytes and they're petabytes at NIH, and actually probably most labs nowadays can or do have petabytes of data from their relatively cheap $100,000 gene sequencer that you can buy commercially. There's a lot of software, most of it is open source, and some of it requires actually large memory. It's a well-known challenging problem to process sequence data and to basically take all these little fragments the sequencer produces and aligns them. And so this particular project is very typical of many, many projects. It's just one of lots of such projects. And this one project has 40 terabytes. Here we have a rather more global discussion of genomics. We're in the metagenomics case, where you're looking at multiple genomes, such as that extracted from environmental studies. Take pond water samples across the world and compare ponds or something like that. And that has even larger data sets. You need to find which genes are in a particular sample, find out their functions, look at the pathways implied, characterize the similarity or dissimilarity between these samples we take from different environments. This is sometimes called environmental genomics. And then we try to work out why these particular changes happened and to relate it to environmental features. And then we need to look at we're obviously going to have these huge data samples. You look at subsamples of particular issues. So they're building, this use case is building a web-based analysis system. And there's a lot of these standard tools which are mentioned here. And they will be accessible through the web. Currently, they use relational databases, and they have 50 terabytes, this particular group of data. Relational databases are already finding this hard. The claim is NoSQL doesn't work so well. I imagine there will be people who might disagree with that and suggest that with properly optimized solutions, NoSQL is able to do this. And of course, this points out real-time interactive use, so that's the streaming aspect of this problem. And also, as the software is open source, it tends to be somewhat flaky and not easy to deploy robustly. Here's an example of effectively the earlier electronic medical records, but applied to diabetes, and also identifying a particular feature. Namely, if you put together all the world's data relevant to diabetes, which is the actual patient records, the information on the disease, the information on the drugs, the information on the drug companies, information on the hospitals, then you get a rather complicated set of heterogeneous data, which this group proposes to convert to RDF, and that actually gives this graph-based structure, which we mentioned as being important. So if they look at this particular case, they point out that the patient record might have 100 areas where there will be a control vocabulary, and then 1,000, so actually discrete entries, and maybe 1,000 continuous values. Most of these values have a timestamp, and this makes it actually processing not really a straightforward SQL command, but actually a relatively complicated piece of mathematics to be able to process this continuous time series data. And you have to calculate numerical derivatives on numerical rate of changes, compare them between patients. And so that actually makes some sort of NoSQL approach with a rather generic user-based, generic processing built on top of it. I meant to say custom-built software that does the processing, calculates all the derivatives, and then finds its derived values to make a comparison between the various data sets. And then, but we still have to process this graph, and this work is with Mayo, and they have to work with an existing data warehouse, which needs to be converted from the traditional form into RDF. RDF comes from the semantic web community, and is a very useful way of representing metadata. So here's another example from a researcher, faculty member at Indiana University, called Statistical Relational Artificial Intelligence, and it's basically taking actually records of typical relational database records and applying machine language and other types of, well, here I call ego global optimization approaches to it. Ego always implies machine language in my classification scheme. His particular work, which his research has done on hundreds of gigabytes of data at the moment, but with a large cohort of patients that could get to hundreds of terabytes to a petabyte of data. And he points out that in some sense you can have too much data, and machine learning algorithms can actually be confused by too much data and extrapolate small coincidences into important deductions that need to be worried about. So this is pointing out that the machine learning, artificial intelligence research behind healthcare is a very vital area, and then these researchers needs to worry about parallelizing their analyses. And so that's non-trivial to do because they're not always trained in that area. Now we come to another type of health study, namely epidemiology, which is study of population scale results. And the typical thing we want to do, there was this famous H1N1 scare where flu crisscrossed the world, and this group and other groups, in fact, modeled this spread, and they did that using agent-based technology. And there's this diffusion of contagions, which are diseases, social unrest, information. So how things move across populations is a very big area of research in the network science area. And they can all be modeled by this agent-based approach, which has been developed by this group. To do this, you actually need to have a synthetic population, because you don't have real people. You would be forbidden probably from using real people just on privacy issues, but you also don't have the data on real people. What you do is have a lot of averages from census information and things like that. And so their approach is to build a set of people which effectively reproduce the averages. And then you use those people to run people-oriented studies as to how disease spreads, which needs information about how far people are apart and things like that. And that's not so easy to do from averages, but if you actually generate a population of people that debase the averages, those people allow deeper questions to be answered. This is a 100 terabyte data set generated for this global population. Is actually a high performance computing application currently with MPI and an important piece of software from Illinois called Charm++. And the parallelism is possible because of the fact that diseases take time to act, and they are intending to extend the use of this type of idea to other examples, which we'll see one in the following use case. So agents are introduced here, and agents, as done here, are an important idea, which is, if we're doing studying materials, then we're going to build that material in terms of atoms or blobs of material, particular pressures and velocities. But if we want to build a model of the world, then we're going to have to take the people as the entity, and people don't obey Newton's laws or Dirac's equation. And so, however, you can make a set of rules as to what people do and then apply them. And so this allows you to build either event-based or agent-based simulations. And this is very famous from the way the military uses to model war games. And it's also been effectively how video games are constructed. They're constructed from monsters and heroes and things like that, which have rules about what happens when a hero does something with a gun and the monster is within a certain distance and so on. These are all evolutions in time which are done according to rules. So that's agent-based simulations, which are very important. So as well as studying diseases, the same idea can study all sorts of things, not just disasters like diseases or earthquakes, what people do. They can study the sort of social consequences of an event like 9/11 or terrorism and things like that. So you can build models which generalize the contagion. And then you can include in that model not just face-to-face interaction, but people accessing Facebook and things like that. So as these same ideas are used to do transportation system modeling, you can actually include vehicles in the simulations as well as people. And you can use this to do critical infrastructure simulations such as power, gas lines, and things like that, internet. And as again, we use these so-called activity models. These are this generate a set of entities, set of vehicles, set of people, which whose act when they're evolved in time, they reproduce the averages, such as those from the sensor. They point out that they have to fuse a lot of data from different sources, and a lot of data is incomplete. And we need to, and also this is not trivial because we're preparing a huge model. We better check that this actually bears some resemblance to reality. So validation is important. So here we have the graph category, which we actually saw earlier in diabetes case, also use graph processing, diabetes health thing. And the idea behind graphs is the following. If you look at a set of data, a set of things, whatever the items make up the data, they're sort of linked to each other typically. And they can be linked in different ways. And in simulation world, things are either linked to all others, that's the all pairs model, or they're linked to people who are near, entities which are near each other, local interactions. That's typical of material interactions. However, you can have much more complex interactions. And so everything's a graph, but the graph category really corresponds to a complicated graph with complex, irregular, possibly time dynamic linkages, which require very subtle processing. Another important category here is the ego category for exascale global optimization, which points out that a lot of these, some of these artificial intelligence problems can be thought of as writing down some sort of function which we need to minimize. And there are various words in the literature such as variational Bayes, elliptic belief, stochastic gradient descent, and a variant of that called LBF, a related method called LBFGS for analyzing these types of large-scale problems to find their minima, multi-dimensional scaling, what I call more generically global machine learning. These are all an important class of problem where a huge amount of data is modeled in a complicated fashion, and you're trying to find the parameters of the model by fitting the data to the model. So that's ego. Here we come to another application, biodiversity, and a European project called LifeWatch. And we know that there's a lot of attention to species, preservation of species, understanding how species interact, and that has a lot of sensor data. And we need to process that sensor, generates custom sensors, integrate all that work together, and whether it be monitoring for species that ought not to be there, migrating birds, wetlands. And there is a project called OMBRI, which actually takes this LifeWatch project and interfaces it with other environmental subsystems so they can share the actual infrastructure needed for processing. So LifeWatch is meant to develop and supply a lot of data analytic and modeling tools, and also to provide workflows that perform particular scientific analyses. And it's meant to provide an opportunity to add different types of data. And there's something called the Global Biodiversity Information Facility, which is the catalog of information has cataloged to find out all the information in this system, which is a very diverse system. And note it includes genomics information, proteomics information, ecological information such as how much biomass there is in the region, what the density of the various populations are, carbon dioxide fluxes, things like that. This is just a huge amount of information. What the amount of algae in the ponds are, and so on. So this is trying to characterize and present geolocated biodiversity-related measurements so that people can study them, put them together. This is a back-end resource to support scientific researchers. So that's the end of the health and medical and life science application use cases. Now we come on to deep learning of social networks as the next use case.